Thank you guys for joining me for this presentation. It's fantastic to be here amongst so many brilliant minds, and there's food and coffee. I'm a data scientist with Surgical Science, and I work in the R&D department out of the Seattle office. And today I want to take you along our journey in the synthetic data for instrument segmentation and surgery, or Syn-ISS for short. First, I'm going to cover a few things, though, that I think will be important for you to know when we dive into the challenge. So, medical simulation is a learning tool for humans and machines, but simulation as a learning tool for machines. What does that even mean, right? So, to help answer this, what is synthetic data? Well, synthetic data is information that's artificially generated rather than produced by real-world events. And this last sentence down here is very relevant to the challenge I'm going to discuss with you today. Data generated by a computer simulation can be seen as synthetic data. So why synthetic data? Well, it addresses privacy concerns, which is very important in fields such as healthcare and the like. It fills gaps. We all know that a lot of real-world data is biased and can be scarce, hard to find. And it allows for the testing and validations of systems in a controlled environment, which makes it more safe. For example, when you're trying to train cars to drive in the real world, it's a lot safer if you do it in a controlled environment first. It is instrumental in scenarios where gathering real-world data is very hard or it's very expensive. We don't have the woman power, the finances, the compute resources, or the time, right? Okay, so synthetic data is very, very powerful, and these are several reasons why. Here's an example of a synthetic data set that we got from a simulator. I'm going to go to my notes here. Through state-of-the-art simulators, for example, like this one that we got this data from, we can generate high-quality data that can significantly aid in training and validating AI models. But also, we can have a scenario generator like this, where we can make our synthetic data diverse, enriching scenarios that are otherwise difficult to come by. So you can see here, we can change the lighting, the fat in this anatomy, or the vasculature. By the way, I do want to mention there are going to be some anatomical images in here, so if that bothers you, some of them are real, most of them are synthetic, but you may not know the difference. And so here's just another example of a customized scenario. All of this is the same scene, but you can see all the ways that it's different. Lighting and exposure, texture. Okay, so AI and digital innovation in surgery. The implications of synthetic data extend beyond just privacy and training. By incorporating AI into surgical simulations, we're not only improving the educational tools for medical professionals, but also enhancing the predictive capabilities of surgical instruments. This initiative is a stepping stone towards safer and more effective surgical procedures, significantly reducing the risk associated with human error. So it's better for everyone involved, most importantly the patients. Okay, next topic I want to cover quickly. What is computer vision? Some of you may be familiar with this field. It's artificial intelligence that uses machine learning to teach computers and systems to derive meaningful information from digital images, videos, and other visual inputs. So, computer vision does power context-aware operating room devices, or intraoperative devices. Context-aware operating room devices are the new frontier in medical interventions. Some of you may have been in surgery recently or in the past where it was robot-assisted. So, AI needs lots of data, lots and lots and lots and lots and lots of data. We all know that. It needs lots of label data. But labeling is expensive, as we discussed previously. This not only takes a lot of time, a lot of money, woman power, and rare events are hard to capture. That, well, it's supposed to be flipping, but it's not. I don't know why. But it would be hard to capture that. So there are ethics and legal considerations surrounding real-world patient data and the like, financial data. But synthetic data is the solution. It solves all of those problems. And we can transfer the learning from simulation to real world. AI applications are already using synthetic data from autonomous vehicles, robotics, in manufacturing and augmented reality. It just takes a quick Google search and you'll find way more than you ever wanted to. All right, so I'm just going to go over a few papers that demonstrate the applications of labeled synthetic data in medical research. If you want to research it on your own time, there are tons out there. Stay tuned for hours. So this paper looks at synthesizing realistic images from virtual reality for liver segmentation. This paper looked at instrument segmentation using 4 kinematics. And this one looks at instrument segmentation using virtual reality. And you'll see why instrument segmentation papers are being highlighted here. Instrument classification using synthetic cataract images. All right, so for the meat and the potatoes, or for me, the fruits and the vegetables and the little chicken, this presentation, the Synthetic Data Challenge 2023. So this challenge really showcases the practical applications and benefits of synthetic data. We hosted this at 2023 PI in Vancouver, Canada. Down here is our website, if you guys care to go and see a little more of what we did there. Here's the organizing team. This is Anand Malpani. He is the Director of Data Science and my boss, my leader. I would not trade him for the world. This is myself at the beautiful Havasupai Indian Reservation. And Mr. Max, he's our project manager. We didn't do this without him. So quickly, what is a machine learning challenge, which is what this was? It's a competition where the organizers, 1, provide a problem statement, 2, typically provide a data set to solve the problem, which we did, and usually provide an award for the winners, which we also did. So Mackay invites challenge proposals every year, and our data science team submitted the following problem statement in 2023, using synthetic data to identify which pixels in the image belong to a robotic instrument and which do not. Now this is called image segmentation. Okay? There are several forms of it, but let's first define image segmentation. It's a computer vision technique and it informs object detection in our case, these images. Machine learning is used to train models to accurately classify the specific types of objects and regions an image contains. I mentioned there were several types, but we used semantic image segmentation for our challenge. This is where a model assigns a semantic class or a class to every pixel in the image. But it does not distinguish between the count or number of items in the image of a particular class. So to help explain that a bit further, right here, these are 2 types of image segmentation. We did what's here on your left, semantic segmentation. The 3 sheep, they're all counted as 1, right? Over here in instance segmentation, these 3 sheeps are each counted as 1 instance or 1 sheep. Again, we use semantic. So for our sub-challenge task, we had 2 tasks. Task 1 was considered the easier task, and it's called binary segmentation. So the models that the participants created needed to be able to distinguish the pixels from the background and the instruments. Task 2, which is considered a little more challenging, we call part segmentation. The models needed to be able to distinguish not only the background pixels, but the different pixels in 3 different parts of the instruments. Here's an example of how task 1 binary segmentation would work. We feed the model an input image, and then it would output a prediction image. And for the binary, it needs to figure out where the background is and where the instruments are. So an example of how the task 2 part segmentation model would work. We feed the input image again, the same one. And then the model would need to predict and output not only where the background pixels are, but also the 3 different types of the instruments. Okay, for a challenge overview, we at Surgical Science created a synthetic data set. We had teams sign up to participate. They created their models, submitted those into a Docker image. We then evaluated those and found our winner. I've got 5 minutes, guys, so we'll speed up a little bit, okay? For our data set source, we used a FlexVR simulator that surgeons train on residents for robot-assisted surgery. And here's an example of a simulator and the synthetic data set that we can get out of it, and we did. Dataset source is an exercise called energy dissection simulation, so you can get an idea of how that exercise goes. And here's our reference generation. This is the exercise taking place over here. And over here, we are overlaying our mask for the background and for the instruments. So for data acquisition, we used Open Broadcaster software, which was for screen capture, and then we used a screenshot plugin to capture a screenshot every second, and these are the images we got from that. And here's an example of our synthetic labeled data set. Here are the images from the simulator. These are the overlays of those images. For our training data, 2 data sets were released. Data set 1 and 2. Data set 1 had 1 scene with 1,200 images, and data set 2 had 3 scenes with 1,800 images. So you can imagine you would want to use transfer learning and augmentation and perhaps some additional data sets. Here's some data set variation examples. We moved the instruments around, the left instrument, then it became the right instrument down here, and we adjusted for lighting and exposure and texture. For the test data set, we added some additional data set variations. Same instruments down here on the bottom of these 2 images, but we used a completely different background. We wanted to see if the models could still find the instruments if the background had a significant change. For participation, our challenge timeline, we released our website, or it became live on May 16, 2023, and participants had until September the 12th, 2023 to submit their doctored images. So they had several months. We had 12 participating teams from all over the world, and we are so thankful for them. I'll cover this real quickly. Models for semantic segmentation can have similarities, even though their implementations and their architectures are different. Quick 3 here, they classify on a pixel level. A lot of them use convolutional neural networks, which are very good with images, and some of them use the encoder-decoder structure, like UNet. That's the model we use for our baseline that I'll get to in a minute. These are all the methods used by the participants. You can see there are many. Some teams use the same method, like these 2 teams use the segment anything model for sound, but there's many different ways they went about it. These are just some commonalities between the methods used. They're large vision models. The participants use data augmentation and real-world data. As long as it was publicly available, they could do that. Evaluation and results. Here's our model. We created a generic vanilla baseline model so we can compare it to the participants. For the binary task, over here on the right, ground truth, our model did very well at finding those instruments. For the parts task, over here, ground truth, and our model did very well at finding those instruments. Our evaluation pipeline, Docker images, we took the models, got their predicted images, combined it with our ground truth and our test CSV, ran those through 2 different Python scripts depending on the task, and output metrics CSV. What metrics did we use? We used to, and I'll cover those real basically, the dissimilarity coefficient is a number between 0 and 1 that tells us how similar the images are. A score of 1 means they are perfectly identical, and 0 means they have nothing in common. The second metric is the Hausdorff distance, or HD. Essentially, it just finds the point where the predicted boundary is furthest away from the ground truth boundary and uses this as a measure of the largest error. The smaller HD indicates that the algorithm or the predicted outline is very close to the ground truth, where the higher the HD is, the more error there is. This is how we process the metrics. You can come back and look at the slides, it's like 1 minute left. Here's our results. X-axis are the de-identified teams. Y-axis is the scores, here's our top 3, all over 0.9, and then it falls off. Task 2, same X and Y axis setup. Top 3 teams, we're at about a little over 0.9 and a little under it, and then it falls off. These are the awards. Task 2, first prize got a lot more of an award because it was more difficult. They got $800 US, and these are the winners. Team MAIA for Task 1 and Team GMAI for Task 2. And what's next? So in 2024, this year, we're currently working on this. Participating teams will assist with publishing the challenge results and data sets. So stay tuned for that. It'll come out and you guys can take a look at our paper. And in conclusion, synthetic data represents a shift in how we approach data privacy, AI training, and healthcare innovations. Challenges like the Syn-ISS push the boundaries of what's possible and create a collaborative platform to solve meaningful problems. The potential to transform medical training and patient care using synthetic data is immense, and the possibilities are truly limitless. Thanks.
you don't have a microphone, but
Okay. I wanted to ask you about the methods that we used by the participants.
yes.
Given how much further transformers and attention perform as compared to other methods in traditional deep learning, do you see a similar performance difference in using transformers versus, let's say, GAN or CNN?
So that's a great question. We are currently starting our work on comparing and analyzing like the images that were output as predictions and scored as correct versus wrong, and seeing like if we can find patterns in what the models were having a problem with which models did better and why. So that will be in the paper though. So that's a very good question. We are about to start that. It's actually on the JIRA board for the sprint. So that is what I will start on tomorrow.
Can I ask one more?
Yes, please.
Anybody, if you know, anybody use WIDS?
I'm not sure. I can go back to really quick. Let me see if I can.
I didn't see it on the list, but.
Oh, if you didn't see it on the list, then no. But I can go back and we can take a look at that together. Should be here. I don't see it. No. Have you used it?
Yeah, so I did, but for my course project,
Yeah.
not for real work like you guys.
Yeah. Did you find that it did well or such? Do you have any pros and cons for it?
It is extremely resource intensive,
Yeah.
and so I used a toy data example, a
Yeah.
data set instead of real data, and it did perform well, but that doesn't speak to anything because it wasn't real data.
Yeah.
My main finding of using it was that you can't run it on a collab.
Yeah.
subscription.
So we had to get one of the higher levels of the collab. We use multiple Databricks stuff, but because, especially with videos and images, it is so compute resource expensive, like crazy. So it's constantly, oh, let's get to this level. No, we need to get more, right? Because the more data that comes in, so that is an issue. So I feel your pain there. Anything else? Yes.
Can you compare these team from the perspective of computational cost and the training data? Are there like specific team that require more training data to achieve a certain accuracy? Or are there any team that's more computational?
Yeah, in our paper that's going to come out, every team is going to have how they approached it and everything put in there. They're actually going to help us write it, because, in order to get their names up there, they have to. If I think I understand your question properly, a lot of the teams did augmentation of the data. Does that answer it? Where they took our training data, which is small, and they made changes to it so that they could enlarge the sample size. A lot of them also used real-world public data, so they went and got public data available that was used for other instrument segmentation, et cetera, and expanded their training data set with that as well. But mostly transfer learning is used, so they took a model that had already been trained, and so it was able to generalize, and then they kind of fine-tuned it to our data to look for specific things like the instruments, right? Because that's really all they were looking for, no matter if it was the parts or the binary. Does that answer your question?
Yeah,
Okay.
thank you.
You're welcome. Yes.
Hi, I know that your contest didn't really focus on the data generation process, but in your view, is the synthetic data generation, is that like a solved problem, or do you have to do this via simulation, and I assume that's where you get your label from the software that generated the synthetic data, right?
Yeah, so it's a little bit of both. We created the synthetic data set. It will be released when we publish our paper, so you guys will have access to it if you're interested. There are a lot of data sets similar to ours that are used in Mackay. So if you look up Mackay data sets, you'll find a lot of cool ones. It was some using software generation, like with the screenshot plugin and the OBS, but there was also me, and I had to go in there and do a lot of manual stuff. So that took weeks. I'm currently working on another data set for different projects. We do a lot of projects, and it's also very manual because it's for LLMs.
And also I'm curious, how do you evaluate like the usefulness of this synthetic data in the real world situation? Like, is it now the gold standard for training surgeons? Is it like getting there? How is it?
Yeah, a lot of for example, like in surgical science, we create robot platforms, robotic simulator platforms, and a lot of hospitals all over the world and residents train on them. There are other companies that do this as well. So yeah, surgeons are using, it's becoming more accepted. A long time ago, when I was younger, AI and healthcare didn't go together. There was a big line there, it's just no way. That's changing fast.
Thanks. We're at time.
Thank you so much, everyone.
Thank you so much.